I mean, so far, nothing's sophistication or communication involved, but now we want to apply the theory to the reality. Okay, so we choose the first get up exercise here in computing sector. We are talking about the hard drive in computer that people using nowadays around the world. Okay, so when you buy a new computer or the new laptop, you expect not to see any crash from your hard drive. Otherwise, you have to replace the hard drive, or you have to fix the error, or in the worst case scenario, you have to buy a new laptop. So this one have some interesting, I mean practical interesting matter. Okay, so we assume that when you buy a new hard drive inside some computer, you have 1% change the hard drive to be crashed. Okay, very tiny amount, 1%, but this is a positive number, not good. So we have to study more. Okay, therefore um, it has to backup. Interesting. One hard drive have to backup. I mean, I go slowly. The first application problem, because in the future you will see that there are so many assumptions in practical application. You should be able to read entirely to fully understand the assumption. Then you go to the second step to models by reality theory, and then the third step you get some result by applying the formula in theory. So there are three steps. The first step is at most one, important one. Understand the full setup assumption. Okay, so one hard drive and then two backup, and the backup has higher probability to crash, and therefore in total we have three hard drive. Okay, but we assume that the three hard drive here are independent. Okay, so that the change that they get the error, they get crashing are independent. Of course, they should be independent in that sense. Then the stored information is lost only in unfortunate situation where, of course, this one happened. Of course, because you have three devices, you have three hard drives, and you back up your valuable data from the first one to the second and the third. Okay, and they are independent. So therefore, if assuming that the first one is crashed, but the second or the third is okay, then nothing wrong, you can recover, you know. So we conclude that by employing the independent assumption, the store information is not only in the case where all three hard drive, all of them crash. That's making sense, right? So you want to know the likelihood or the chance that the information is zero. So that means we define the worst case scenario here. Your data is fully lost if the three of them, you know, crash, all of them. So we will need to know the case where we have the information is zero. That means you can recover either from 2 or either from 3, etc. Or of course the first one not crashing. Okay, so this is the full assumption. And how can we solve that kind of problem? We need to apply the theory. Okay, step 1 then understand. Step 2 modeling. Modeling is the second step, and this one in applying discrete probability, the most important one is defining the event. Because before you can compute anything, you need to know the event. So we define the first event here, I call capital H, saying that your first hard drive crash. Because you buy this one is the first hard drive. Then because they are independent, therefore we define B1 to be the event. Don't forget the bracket here, because we define the event to be a subset of the symbols B, remember? So So B1 is the event that the first backup crash, and because you have two backups, so we also need to define B2 like this one. Okay. So you have the three events here associated with the case of three hard drive crashes. And we know from the assumption that the H, the B1 and the B2 are independent. That's fine. Moreover, we also know particular value of the three event, the likelihood to get crash 1% here for the first hard drive, and this one means for the second and the third hard drive. A little about the notation. In my lecture, we employ the probability of event by using three different notation, but they should be the same. Okay. If I give you one event A, and we know this one, we call the probability that event A occur. This also can be written down by using the second notation like this, where I replace the bracket by the square bracket. This one is the most beautiful one. Then you will see later on, most of the case we employ the square bracket when we talk about the probability of event. But the original one, I mean mathematical sense, then in some cases, in particularly in some problem, we also use this notation. The last one is the most ugly one, okay, not beautiful, but we also use. To me, I refer the middle one. You will see, I will try to use as much as possible. But the three notation here play the same role. They indicate the probability of event A. Okay. So now, so far we got, revise or review every assumption we have. Now we compute. Okay. We move to the third step. We apply the rule. Because you say that you want to know the probability of information can be saved. That means we can define the event of your interest will be just like this one. This is the event. We apply very short term like this. Okay. So actually, this is not good full answer. I mean, if I can define E like this one. I say, okay, this is the event. I have to write the full sentence. Okay. And you say here, your information is saved. So this is the a better way to define the new event before you can compute. Okay. Define event E to be the one bracket here, information is sales, and then you put the bracket at the end. Then the left hand side here means becoming P of E, and the complement event. The complement event defined to be the negation of the original event E. In terms of math, you say here the anti-sample space. We don't write carefully, but we know the negation of E, and then the negation of E will be denoted by overlay of E, or in some textbook they also write E with the power C on top here, mean the complement of E. Okay? The complement means the negation of this predicate, so we say E complement means information is lost, so that's why you have here. Okay, so this one is the probability of the event E complement actually. And actually we are employing one of the axiom by common group. See that? So P loss means P of the complement E, like this one. So PE equal to 1 minus BEC. So this is the consequence or the result of A3, HCM A3. Then we define the event of losing data. Losing data, the data is lost if one of the three hard drive crash. So that means the event H must occur, the event B1 and B2 as well. They are all occur, they are all crash. They intersect together, making the EC. So now you understand. The EC, that means the data is lost, actually including the equal to the intersection of H, B1 and B2. That's all. And finally, we employ the fact that here they are independent. You follow me, guys? Good. Lê Hoàng, you sit in the classroom alone. Only you. You and Lê Hoàng, correct? 3 guys I see in the classroom. And where are the other guys and ladies? Where are they? They sit in the same room, but at the corner, different corner, right? Tell me, Hoàng. Lê Hoàng, huh? Right? Is that you, right? Yeah, only 3 guys. So why not sitting in the first day? Okay, so right now I see in the class there are 31, 49 total. So not good compared to last week. So remember, the structure is one of the most difficult subject in computing. Okay, sometimes the number of students fail in this course may go up to 75%. 3/4 can fail. Okay, so tell your friend, don't look down to this course. Okay, in the history of the faculty, 75. So be patient and be, working hard. Don't miss any lecture. So try not to miss any session. Nguyễn Hồ Quang come in almost 30 minutes late. I don't know. I asked you to be on time, but Nguyễn Hồ Quang. Some beautiful name I will keep in my mind. Okay. So Quang coming late, is that correct? Hồ Quang? Good, yeah. But you asked permission here 9:29, very late. Go to the class with wrong email. Okay. Understand. Okay, thank you. Sorry for that. Wrong email. Okay. So the complement C means the data is lost, and losing data happen if one of the 3 hard drive crash. That's why you see the intersection here. So everything must be interpreted correctly so that you can get the right event. Okay. Then we employ the fact that the 3 events are independent, and probability theory. If you have independent event, then the product of their probability equal to the probability of the intersection. Okay. So finally we get this one. So to me, question number 6 is also beautiful because that illustrates really the modeling process in computing in your career. Okay. you have to write down some assumption review, and you have to use some right formula, and you have to apply some logical argument. So that's the whole procedure. Now let's see the question number 7. So I think you have to follow the same methodology. Okay, first, step number 1, fully understand the whole data, okay, the assumption. You have to read, because you belong to international program, so everything written down in English. So we talk about the multiple choice quiz, and we define a problem in that kind of quiz to be answered correctly with the probability 90% here, 0.9, if the student is prepared carefully. Then we move to the next assumption, saying unprepared student. Guess between 4 possible answers. So that means the case where your friend, he or she did not prepare very good before the day of exam or the day of test. Therefore, when they enter to the exam room, there is only one way for them. That means they're guessing, okay? They don't know the theory, so they have to guess, and they get among the 4 possible answers. Usually, the lecturer provide A, B, C, D, so you have to choose only one. And the unprepared student guess, and because there are in total 4 choices, then the probability of choosing the right answer is 1/4, obviously. So there are 2 assumptions. The first one about the good student, prepare carefully at home, then the chance for good student to get the right answer is 90%. But for the not good, so student, because he gets, so there are only 1/4, which is about 25%. And what is the last information here? Do we have? Yes. We talk about the 75% of students. So we get another saying that the full class, I don't know how many students, but they say 75% of the whole class prepare carefully for the quiz. So also practical, I think. Now, if we assume some specific student, we say Mr. X. We don't know. We just say randomly, okay? Any one randomly. Let's say Mr. X. He give a correct answer to the problem. Then we need to know what is the chance that he did not prepare for the quiz. So this problem is very interesting as well. We provide some number about the probability of choosing right answer, etc. Now we assume some abstract guy, arbitrary guy, assuming that he give a correct answer already, and we need to know the chance that he did not prepare for the quiz. That means the probability that he is not good student, he did not learn the theory, but he still give the correct answer. So maybe this is one interesting for you. Do we have that solution? So only one way, modeling and computing and get the conclusion. In this case, you have something, in the modeling step, differ from the exercise number 6 before, okay? So, because the last question asking you that, so that might, trigger, that might make you think about the conditional probability. So question number 7, we talk about conditional probability. So this is one of the most important concepts. So I have to write here. And about the conditional probability, then there is no way you may avoid Bayes theorem. When you see conditional probability, then you should think about Bayes theorem. Okay, so how can we apply this one? Interesting. So he Mr. X, and we assume he choose correct answer. So we can say, or we can define this one to be event B, and then we would like to know the fact that he is not prepared carefully at home before the exam day. Then we may define this event to be A. And if you do the written exam, you have to define A and B carefully, okay? You have to say like, let A or let B be the event that Mr. X, we define A and B before you can employ. Employ the event. Because without this one, when you get bigger problem and longer and complication more, then very sophisticated and lengthy problem, then you lost the way to go. So defining the event by capital character is good for you. So we define that one, and also we define A by the same idea. Okay. Then you can compute some relevant, probability. So the event B, to say that Mr. X is not prepared at home. Okay, event A, say in that Mr. X not prepared so good at home. So we have two event A and B, and we want to know by the question that we want to compute the conditional probability like this one. You have to define clearly your objective in your mind. You have to write down that one before you do. And this finish the first step. We're going, revising the assumption. Now we get 90% for the case that some good student they prepare at home and also they get correct answer. In terms of mathematics, that information tell you the second conditional probability. You see, I go slowly because this is the first time you see modeling. Modeling is as most important for your career. You will see. The student get randomly, correct answer if he prepare good at home. So that means the second one also conditional, but now the condition now turn out to be the A complement, right? Because Mr. X not prepared, if I to be A, then if he prepare good, that means A complement, and also he get good answer, correct answer. So that means we get this one, the first. Okay, look in the chat box. That gives you the second line here. That's one. You see? So we define A in the first question to be the original one, but in the second line in the solution, the condition turned out to be complement of A. Complement of A. Because A defined to be not repair, so complement become repair, good repair. And correct answer still keep to be B. Okay. Now, what else do we say? What is the meaning of the third row? Who can tell me? Who can answer this one in maximum 2 minutes in terms of symbol? And if you provide a good one, then you get bonus. So someone answer me, Nguyễn Hồng Quang or Nguyễn Quang? Nguyễn Hồng Quang, right? Nguyễn Hồng Quang, good. So let me check. Let me check that. Nguyễn Hồng Quang confirm that the third row mean this one. 1/4 means 0. So we read that one, okay? The condition mean not repair, not repair, not repair. So that means A, find the condition, and then correct answer mean the event B, because we define B to be the correct answer. So that 5. So Nguyễn Hồ Quang will get 1 bonus point. Good. And the other one, I mean the two final here is easy because this one is not conditional, because we know that 75% they prepare good at home. So the complement will be like this one. Vinh, Lô Quốc Vinh. I see. Vinh and Wang give the same time. So I see. Sorry for that. I got the information now. Agree. When on, so get that 1 bonus. Good. So far we have everything. So I think that we can try the event here in the row here to be the event E. I mean, try not to duplicate the event, and not prepare turn out to be the complement. Okay, so you have got all notation for the number. Now you can compute the probability of the event A. So this is the one we are working now for the next step. Computing event A we define to be, event B, sorry. Any student. So we apply the total probability theorem. This is the name of total probability theorem. And you know from the class, okay? So you decompose the event A to be BA, then union with BAC, right? And then you apply that formula. To me, symbol is very convenient way to write down solution. Because if you define only one, but you employ many times, you see. So I am trying to help you thinking that mathematically, the union of event, when you move to the probability, you have to change to be the sum of number, right? And this is the one you see in this row. You see that? So actually this one is B, and this one to be a complement, because we define not repair. So therefore, repair become a complement. And the not repair here become the event A. Actually, and of course, this is event B intersect with AC, and this is event B again, then intersect with A. So basically the information right here in these two lines are called alpha. Let's say alpha is the one I brought in the chat box. You see there? And finally you can compute the answer, okay, by applying the John distribution with the conditional. Do you know the conditional, right? So the product, this one equal to, well, remember, this is the product of B condition A multiply with the one like this one. Because the left hand side tell you the John distribution up to event B and A equal to the product on the right hand side. So that is the first component down to here. And then after the plus here, you get the same idea, but for the second part, actually. So the two become like that. And you take the sum and you get the answer. And that finishes this exercise. Okay? Are you fully understand? Do you fully get the idea? So in the solution, actually we did not, in the ordering, okay, repair, good repair mean AC, and not repair mean A. So that means I have to write exactly that one for you, okay? And you know the two conditional probability before you get plug in the value, and that finally we get. So you have to put some intermediate step of computation here before you get the answer. And then this one tell you why this one, because we compute in the probability of event B, but the last one is not event B. You see, what is the notation for the last one? Tell me. 1 minute. What is the symbol for the last row here? 1 minute, and tell me. Up here in the alpha, we compute the probability of event B only, raw. Okay, correct answer. Wang say something, the last one. No, this one is not good, Wang. Why so complicated? Bảo Ân, Trường Thịnh, Quốc Vinh. Now stop, okay? So I got the three answers. Stop sending answer, I will explain, okay? Bảo Ân, Trường Thịnh, and Quốc Vinh give the same answer. So let me check. Good. So they say that the last one mean a condition with condition B. So if we interpret explicitly, then A mean not repair. 5. Correct answer mean B. 5. Good. But where do you get that one? because you are right. You give the formula right. But why do we get that number? Because in the previous step, alpha, I computed for you this one, right? We done that in the alpha. Then we got this one. So that means you have, I want to see the full formula of your conditional probability before you get the number in the right hand side. I would like to see that formula. Not only the PA over B, but also implicit formula for that. Ân, Thịnh, and Vinh. Can you? I would like to see the concrete formula, the full formula, so that we get the right answer at the end. Yes. Is that one conditional as well? Yes. But what is the formula there? What is implicit formula? Bảo Ân go first, so stop. Let me check. Okay, why that one? No, not the answer. The other guy continue. Bảo Ân. Quốc Vinh. Yes, so Quốc Vinh get the point. So Quốc Vinh get 2 points today, right? Quốc Vinh, at the beginning he got 1, now he got another. Totally he got. Thank you. So the right answer is on the chat box. Quốc Vinh. That's fine. The left hand side is conditional, and this is the conditional probability. Therefore, you apply the definition. Yes, we have the ratio of the Jones distribution on top and divided by the other one. But I asked Vinh, only Vinh, because you write the one here. Do we know P of A intersect with B? Did we compute that before? When? Intersection. Yes. So what is the value of that one? Intersect of A and B. Where do we get that? In which formula? I don't see from the solution so far. The second component of the P correct answer, the second component good. So that's the product A and B. But do we know? Do we know that component? The value, I mean. You are right. You are right when you answer that, but do we know the value of that? Do we know the value of that? You are right. The second component of that one, 5. Yeah. So when answer, the number will be the product of 1/4 multiply 1/4. So this is the answer. Right. So very good answer. I will help him to write the last answer on the chat box as well. In terms of notation, it means that you have to change the role of A and B again. You see what I mean? So he apply this one, and we know this one, and we know this one. From the information there, we get this one. So that's the answer. Be careful, Vin. Double check the final before we move on. Double check the final before we move on, Vin. So not prepare 104, good. And then the conditional B over A. The conditional B over A mean right here. So that one mean the probability of the event B not repair over A, and we got 1 over 4, and also we know the probability that the student not repair also 1 over 4 here. So when double check and he answered rightly, so we got finished this exercise. So you have to write the full answer, everything, okay? Everything. I mean, there are some certain thing here you have to explicitly write out so that you get the final answer. If you don't see clear, you can ask when after the session today. So we finished the solution, and maybe I try explain the last one in this exercise set for you. So I skip this one, I don't explain. I skip this one. You have to do yourself a lot of a few more exercises. I only choose some specific important application only, okay? So I would like to explain this one for you in the last 5 minutes in the first hour today, because that may be important for computing students. We are designing a Bayesian email spam filter. You know, nowadays a lot of junk email, bad email go into your email box. So therefore, as a computing student, you should design some filter to remove the bad email. And the mechanism to define or to design that filter is based on discrete probability. Actually defined based on Bayesian theorem. So you see that's why this problem is interesting. So we have to train your filter, email filter, on a set of 500 spam messages. I mean good messages, okay? And then, okay, sorry, total 500 spam. That means the bad email here. Spam means not good. Spam email means the bad email, okay? Bad email, not good email. And not spam, that means good email, okay? So we consider the filter to delete out the spam. That means delete out the not good email, okay? And we train the filter by providing 500 spam and 200 not spam. Fine. And how can we do? Only one condition here that we can rely on. In the future there are more, but right now we start very simple. Okay, by looking to the word exciting. In the future maybe the images or something else, but right now let's say one single indicator exciting appear in 40 spam, and the word exciting also appear in 25 good email. So there are a few numbers you have to employ later on. You see, 500 in total spam, 200 not spam. Okay, but the filter will look to the word exciting. Okay, and they see. I mean, the filter will see that the word exciting appear in the 40 spam, but only 25 not spam. So that is the information. Then this is the question: would incoming message to be rejected as spam if it contains the word exciting? We assume that your friend sent you a good email, but he or she brought in the email this words, and the filter by default detect this one, and the filter have to make a decision, either reject or accept. And the response for rejecting will be this number. That means the filter will compute. The filter will compute the probability. Compute the probability. To decide your email to be spam or not. And if that probability bigger or equal the response 90%, you see what I mean, then the filter will reject your email or your friend email. But if the probability get the probability be only let's say 65, then that means the filter consider that one is good and not reject. Okay, depending on the outcome. Okay, with the chat box. So we need to compute again some probability. So we have to define. So this is the beginning story. We have to define the event that message is spam by symbol us, and the next one will be the event that the message contain the word exciting. So actually you have two events you have to define. That one, spam mean us, and message containing this one to be E. So because your friend email already consists the word exciting, that means the event E turn out to be the condition. Very clear, right? And you want to decide your friend email is spam or not, that means you need to compute this conditional. So the answer here is yes. After you define carefully the two events, then your objective will be this probability. This turned out to be a conditional probability, not the raw probability. If someone of you say after you define the event us, and you say I want to compute P us, then that one is wrong answer, because that one does not reflect the information right here. The information right here saying that you want to reject that email to be spam with the fact that the email already consists of the word exciting. So with that fact, that means you have to put the condition here. Don't forget that. So that's the beginning of the story. Now, we don't know the probability for some incoming email to be spam. We don't know because so far here we have that we provide the total number of spam messages to be trained and 200 not spam, and also we count the words exciting in 40 spam and 25 not spam, etc. So we don't know the overall probability that some incoming email to be spam. We don't know. So that means we have to assume. So this is extra assumption. We assume that any email coming to your server, let's say computer science engineering faculty server, 50%, that means 1/2 to be spam because they are random messages, okay? Then if the event here 1/2, then the probability that message to be not spam will be the complement of that. So 1/2 means 50%. So we get the second one on. So 1/2. This means 0.5, 50%. So fair, balance, because we don't know the information. So we have to assume that one. We do not know anything about the general probability of incoming message to be spam or not. So they will have to assume that one in overall. Okay. So this is the full information. We need to find this one. And again, to find this one, you have to apply the definition of conditional and also sometimes the Bayesian theorem as well, the Bayes theorem. So this one, this one actually we rely on the event us here, yes. So very lucky for us that this one will be 0.5. We define event us, now we apply this formation right here. Then we also get this one to be the probability of the complement us as well. Spam, us means spam. So therefore we get the equation right here. Now the other information you have to employ that you train the filter by providing 500 spam, but the event that the filter detect from information there, the event successfully detect the spam only 40, you see. So that gives you the second conditional, okay. Assuming that 500 spam, because this one is the set of spam email you train the filter, that one. This one happening already to be the condition. Then this is the event E, mean the word exciting, you see. So we can say the probability for event to contain the word exciting actually turn out to be this conditional. And this number by combining the two numbers up there. Is that clear, people? Right? So we know that one. That's fine. Okay. To contain the word exciting in the message already known to be spam. And again, you also train the filter by providing 200 good email, good messages. But among 200, you also, the filter successfully, or I don't know, unsuccessfully detect 25 with the word exciting. Again, by the same argument, a message contains exciting words, but belong to the second group of the training set. Okay, training set now to be 200 not spam email, you see. And by the same idea, you have here, guy, tell me, this draw correct or not? This is the critical question. 30 seconds. That formula is correct or incorrect? No. Phạm Châu Thanh say no. Excellent. But what is your answer if you say no? Let me check. San, Tan say again. Tan say again. So let me copy his answer and we check before I give his mark. He said that the number 25 over 200 will be that conditional probability. So that's correct. So in this case, the condition happening to be not spam, and not spam mean the SC, the complement of us, correct? And you want to count the word exciting, that means the event E. Okay, the condition us complement, fine, because that is known to be or not known to be, that's fine. So Phạm Châu Thanh. So today Vin got 2, Thanh got 1, and the other guy. So there are 3 people got bonus today. Let me check. Vin, before Vin, who got another point? Wang, huh? Right? Yes. So Wang 1, Thanh 1, and Vin got 2 today. Okay. So you have to change here. So this is my intention to write wrongly. Now due to Thanh who fixed that error, this one turned out to be a C, not a split. This is a C, right? Fine. Or complement of us. So finally you can answer the objective. Okay? This is conditional. The work already inside your friend email and you determine that one to be spam or not. And this is the truly bias formula. Bias formula. Okay? Then the upper is like this. Huh? Right? And the one here, in terms of the bias formula, what is the denominator? Very long, but what is the short term for that, guy? What is the denominator here? This one, right? Correct? And the answer is yes, yeah. And that event again can be decomposed to be like this. And then you get that one in the denominator. You see? And every information you got, you just plug in and you get this one. And we get this one smaller than the threshold. Therefore, your email, your friend email, will consider to be good email. Okay? So this is the final answer for this. So Bảo Ân asked me a question. That's very good. Why can we take the PS? So very good question. So let me explain the question by Bảo Ân. He said that why not we define? Very good question. Thank you. I very like question. You know. Bảo Ân said why? Why don't we define the PS like this one? People, pay attention to the chat box. I am explaining that. To him, Bảo Ân, he think that the probability of the us mean the spam, must be 500 spam email divided by the total the spam and not spam. Okay, you see there. So this one, this value, the answer is this value is based on this value. This is the short answer. Just one instance of the very good question. So I explain very carefully. Generate probability PS. So we don't use that instant because you gave the filter, the training set with 500 spam and 200 spam. That's considered to be a special case. In the future, you may define another training set. Understand me? So in the future, you may define the new training set. Let's say you have a larger, okay, uh, 1,000 spam email, and then 3,000 not spam email. Then you have another instance. Meanwhile, the notation we mean the generic, I mean the population, entire whole population. Okay. So we just define for whole population of spam and not spam. So we don't know that value. We don't know. So that means we have to approximate by the 50% or must assume for that one. Okay? We don't know. So we can approximate by the two number I give you, but this is not a precise. The precise answer is the generated BS cannot apply for specific cases, but assumed to be 50%. So because the question very good, so I give the question is good, so he also got one bonus, and then we finish the first session, and we have 10-minute break, okay, and we resume at 10:28. Okay, thank you.